Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate. Why are we interested in water vapor pressure when we know that water vapor is less than 1% of the air that we breathe? 78% of the air that we breathe is nitrogen, but we are not interested in nitrogen vapor pressure. We are interested in water vapor pressure. The reason is that water vapor is the only gas in the atmosphere that can condense at environmental pressures and temperatures that we have in our atmosphere. All other gases, nitrogen, oxygen, argon, and so on, only exist as gases in the atmosphere, whereas water can condense, can freeze. In other words, can change all three phases in the atmosphere, and when water is changing phases, energy is either released or taken from the system. And that is why we are interested in thermodynamically examining water vapor rather than nitrogen vapor and so on. Now, how do we do it? We know from my previous video that total mass of air in this room, for example, can be split in the mass of dry air plus mass of water vapor. And as I just outlined, this mass of dry air is mass of nitrogen in the air plus mass of oxygen in the air plus mass of argon in the air plus 3 dots. All these together are dry air, and plus mass of water vapor. Similarly, we can split the total pressure into the pressure of dry air plus pressure of water vapor. And this is called Dalton's law of partial pressures. By convention, we do not write PV for water vapor pressure. It's just convention, we write E. And again, what is this? Well, pressure of dry air is pressure of nitrogen plus pressure of oxygen on your body or on whatever else, plus pressure of argon, plus all other gases, plus pressure of water vapor. This over here is this pressure of dry air, PD. Okay? This E, namely this E, is known as partial pressure of water vapor. Partial because it only plays partial role in the total pressure of the air. So what we can also conclude, if we have, for example, total pressure in this room 1000 millibars, which is also 1000 hectopascals. As you know from my previous videos, 1 millibar is exactly same as 100 pascals or 1 hectopascal. So, if we have this pressure in the room, which is very likely, for example, or around this value, we know that nitrogen is 78% of the air. Oxygen is 21% of the air. Let us assume there is no argon. So 78 and 21 is 99, and let's assume the rest of the gas in the air in this room is water vapor. Well, that means that out of these 1000 millibars of pressure acting on my body, 780 millibars is pressure due to nitrogen. 21%, well, that would be 210 millibars, would be pressure due to oxygen molecules in the form O2 in this room. And only about 1%, which is 10 millibars, would be due to water vapor, H2O, in the air. So you can see, in terms of the total pressure exerted on our bodies or exerted on any object, water vapor pressure is very, very small, not more than 1% of the total pressure exerted. Mostly it's pressure of dry air, primarily nitrogen and oxygen. But as I said at the beginning of this video, we do not care particularly about thermodynamics of nitrogen, oxygen, argon, CO2 and so on, because they always stay as gases, whereas water vapor can change to become liquid water or solid ice. And this is where the concept of saturation vapor pressure kicks in. To discuss saturation vapor pressure, we remind ourselves that E is partial water vapor pressure. Saturation water vapor pressure tells us, very important sentence, how much water vapor needs to be in a parcel of air to have condensation. And this is saturation water vapor pressure. Namely, when E is equal ES, we have saturation. What does that mean in simple words? That means that if we add even a little bit more water vapor to that volume of air, we will have condensation occurring. How can we explain this in even simpler words to kind of visualize when the system will become saturated? The easiest way, in my view, is to do the following. We examine 3 cases. Case number 1, here is a container that has solid lid, okay? And in this container, we have liquid water and we have dry air. Imagine this is figure A at time t equals 0. There is no water vapor in this air. Volume is fixed because we have a lid and we have liquid water. What will happen in this case? Well, in this case, we have molecules of water over here clearly. Some of these molecules will evaporate and go into the dry air. Which one are most likely to evaporate? Well, in order for this molecule to evaporate, it has to have enough kinetic energy to break hydrogen bond between this water molecule and the rest of the water molecules that are surrounding it, as I discussed in my video on why is water so special. So, from the probabilistic point of view, molecules that are going to evaporate are most likely those molecules that have high kinetic energy. And we know that kinetic energy is proportional to temperature. So the molecules that will evaporate from liquid water are most likely to be those that jiggle a lot. And these are molecules that have high temperature. So as the liquid water is evaporating into this initially dry air, the temperature of liquid water is decreasing. Why? Because the most energetic molecules of water are the most likely to escape. And the most energetic means the one that carry highest temperature. Because kinetic energy and temperature are related, as I discussed in my previous videos. Another important thing to mention here is that we do not have equilibrium. Notice that in this particular case, we have 3 molecules evaporating but no condensation. So the process is only in one direction. We have evaporation that dominates. Now let us look into this case after some time. So we have the same container. We have this solid lid. It is very important that the lid is solid. Nothing can come in or leave. And in instant B, we have T equal T1. Some time has passed. Now, a little bit of this liquid water evaporated, so the grade line of liquid water will be lower compared to here. But now we have moist air. Okay? We don't have initially dry air. We have moist air because these molecules evaporated. So we already have now some molecules of water vapor in this volume of air, and more molecules are also evaporating. But there will be now, this is important, there will be some molecules of water vapor in the air that go back to liquid. Namely, there will be some condensation. Now, let us assume that at this time, T equal T1, there are 3 molecules evaporating, as I indicated, and 2 molecules condensing. So the end balance is that we have net evaporation. 3 evaporating, 2 condensing. 3 versus 2, we have net evaporation. But the last figure is now going to reveal the concept of saturation vapor pressure. We have now the same container in the last instance with this solid lid on the top, because in instant T equal T1 we still have net evaporation. That means that this liquid water line will still decrease a little bit compared to the previous case. But now we will have perhaps 3 molecules on average evaporating and 3 molecules on average condensing. This means that this air is now saturated. Okay? In this case, we have dry air. Partial pressure of water vapor is 0. There is no water vapor. Here, we have moist air. Partial pressure of water vapor is some value E. Here, we have saturated air. Partial pressure of water vapor is equal to saturation pressure of water vapor. Very now important sentence. When we are below saturation, case B, when we are below saturation, we still have condensation, but the rate of condensation is lower than the rate of evaporation. And overall, net, we have evaporation. When we are in figure C at time t equal T2, we still have evaporation, but the rate of evaporation on average is equal to the rate of condensation. Or in even simpler words, on average, for every molecule of water that evaporates, there is another molecule of water vapor that condenses. And that means that the system is in equilibrium. Why do we call it equilibrium? Because the rates of evaporation and the rates of condensation are the same. This over here is not equilibrium. Now, you can immediately see that this saturation vapor pressure, and very, very important, saturation vapor pressure depends on temperature. Why? Because if we increase temperature of liquid water, then there will be more high energy molecules of liquid water that will now tend to evaporate. And we broke equilibrium. After some time, T equal T3 perhaps, there will be new equilibrium. But at that new equilibrium, at higher temperature, there will be more water vapor molecules in the air. So, as we are increasing temperature, the saturation point of water vapor in the air increases, because there is more and more liquid water molecules that can escape liquid, and consequently there can be more of them in the air. So the equilibrium moves as we move temperature. At lower temperature we have very low saturation. At high temperatures we can have very high saturation points. In the next video I will discuss exactly how this saturation vapor pressure depends on temperature. There is a curve that very nicely explains that functional dependency. But in this video, I don't want to make it longer. I hope you can understand the concept of partial pressure of water vapor and saturation pressure of water vapor. Lastly, here E is 0, here E is less than ES. Here E is less than ES. Here E is ES. Is it possible for partial pressure of water vapor to exceed saturation pressure? Answer is yes, for very short transient periods. That would mean that we have actually overall net condensation. And that overall net condensation will result very quickly in new equilibrium where the pressure, partial pressure of water vapor will reach saturation pressure of water vapor. This is the concept of partial pressure and saturation water vapor pressures. Please make sure to like and subscribe, continue watching Fundamentals of Weather and Climate, and until next video, goodbye.